Hi all, welcome back to a brand new video here with me. In this video we're going to solve and explain an astronomy problem by the name of Count With Me. So in this problem they have an A0 spectrum star. It is theoretically able to be seen with the naked eye, but because it's dim when we see it with the naked eye, or it's quite unclear, so we prefer using a telescope. The telescope that we're using in this case it has a radius of 0.25 meters and an efficiency of 0.4. So the star is moving away from us with a velocity of 0.6 c, or the way you can put it is c is speed of light in vacuum. So it's moving away from us with 0.6 times that speed. So how many photons pass through the eyepiece every second? And we have to detail the assumptions that we used, which we will see. We will have some assumptions here. So first off, we assume that the magnitude of the star is 6. Now why 6? Because as stated earlier, we can see it with the naked eye, which means it's less than or equal to 6, but since we're using a telescope and since it's quite dim, just assume that it's 6 because not all nights are clear. Then we can just compare it with the flux of the star and the flux of the sun, which we know. We just need to use the Poisson's logarithmic, right? And we will see that the flux of the star is equal to 10 to the power of the difference in magnitudes divided by negative 2.5 multiplied by the flux of the sun. We plug in the numbers that we know, which is magnitude of the star, sun, and the solar constant, and we will see that the star has a flux of 1.097 times 10 to the negative 10 watts per meter squared. Now we have to find the power of the star that reaches the objective lens of the telescope, which is just the star's flux multiplied by the areas of the telescope, or in this case it's a circular telescope, just pi r squared, and we will get that the power of the star taken by the telescope is 2.155 times 10 to the negative 11 watts. That's at the objective point of the telescope. The next assumption is we assume that the temperature of the star is equal to the temperature of Vega, which is 9602 Kelvin. Why do we assume that? Because it was stated earlier that the star is an A0 spectrum star, just like Vega, and A0 refers to its temperature, so we just assume that it's the same. Therefore, since it's a black body, we can use the Wien's law, or we can say that its wavelength multiplied by its temperature is the constant, which is the Wien's constant. We know the Wien's constant and we know the star's temperature, so we can just use that to find the wavelength emitted by the star, which is 3.018 times 10 to the negative 7 meters. Now, the speed that's moving away from us can be used as redshift. Why so? Because it's moving away from us, therefore its wavelengths will be more shifted to the red part of the spectrum. Now, since we know that its velocity is big, and we assume that it's one system with the Earth, therefore we use the relativistic redshift, or z, the redshift, is equal to the square root of 1 plus beta divided by 1 minus beta, all of that subtracted by 1, where beta is equal to v over c. And we can simplify that by moving the 1 to the other side, and we substitute the beta, and we will get that z plus 1 is equal to the square root of c plus v divided by c minus v. And we know that v is equal to 0.6c. When we plug that in, we get that z plus 1 is equal to 2, or the redshift plus 1 is equal to 2, or you can also say that the scale factor is equal to 2. Now why is that important? Well, z, or the redshift, is equal to the change in wavelengths of the star, or we can say it's the wavelength action of the star divided by subtracted by its real wavelength, the emitted one from the star, divided by the emitted wavelength from the star. So what do we know about this? The wavelength that we observe is different from the wavelength that the star emits. So we can simplify that equation. The z will equal to the lambda action of the star divided by the lambda star minus 1. We move the 1 to the other side and we get that the lambda action of the star divided by the lambda nil of the star is equal to z plus 1, or that the lambda action of the star is equal to z plus 1 multiplied by the lambda emitted by the star. And this is all because of the redshift, because it's moving away from us. Now, what do we get from this? Well, now we know that the efficiency multiplied by its power is equal to the number of photons multiplied by the energy of every photon, or hc over lambda, all of that divided by the time as well. Now hc here are constants, p, or the power of the star we found earlier, and the lambda action of the star, which we can see on the left side, and the efficiency on the problem, it says that it's 0.4. Therefore, we can put this here, and what we're supposed to find is n over t, which is 2.617 times 10 to the 7 photons per second. So we will find that many photons passing through the eyepiece every single second. Okay, that's all for this video. Hope you enjoyed and learned something new. The presentation for this video, I'll give a link in the description. Thank you.